Hi everybody, Professor Rad here. So I'm going to go through two different types of examples that I got email requests for. First, I'm going to do a few examples of graphing rational functions, and then I'll do a few examples of solving nonlinear inequalities. So once I get a chance, I'll put timestamps in the description below so you can kind of skip around to the examples you think will be most helpful. And after I film this, I will scan these pages and upload it as a document to Brightspace as well, so you can reference that as well. So in these examples where we graph rational functions, I've basically got all of the prep work done. We're just going to go through how do I use this information to graph the rational function. So for this first example, f of x is a rational function with 3 x-intercepts and a y-intercept. It has 3 asymptotes, one of which is oblique, and then they gave us a table of signs to help us figure out how to plot points and such. So let's start out with the points that we know, and then we'll do the asymptotes, and then we'll try and figure out how the function should look. So we have our 3 x-intercepts, -3, 0, -2, 0, and 2, 0. So I'm going to go ahead and graph this now. I didn't have any graph paper handy at home, so I just did my best to create a grid. So we'll do our best graphing this, but we'll know it'll be a little bit shaky. So I'm going to graph those 3 x-intercepts, -3, 0, -2, 0, and +2, 0. And then the y-intercept was 0.8. So that'll be right here, right? 2, 4, 6, 8, 10. Yep. Okay. And I guess I should have said if you want to take a moment and copy this example down, you can as we work through it. Then I'm going to graph the 3 asymptotes. So remember, whenever you see x equals, that means it's a vertical line. So I'm going to graph a vertical asymptote when x is -1, as well as when x is 3. So I'm going to turn my page here a little bit to graph this. But here x is -1, so I'm going to do a dotted line there. And then x equals 3 was the other one, so we'll kind of graph that one here. Okay, and that is what I would call the easy stuff out of the way. So the easy stuff are the points that they give us. Just make sure you graph those properly. And then vertical asymptotes are easy because you just put them where they need to be. The oblique asymptote, we're going to have to work on a little bit. So let me get another color for that one, just so we can practice graphing the obliques. So this is y equals 1/5 x plus 1. So the oblique asymptote was given to us in slope-intercept form. So this is our y-intercept at 1. So I can go ahead and plot a point here at 1. And then the slope is 1/5. So I'm going to move up 1 unit and then to the right 5. And I'm going to keep doing that as long as I can, or I could go down 1 unit and to the left 5. Now, I have to be very careful here because my scale on my x-axis is different from that on my y-axis. So when I go over 1 space horizontally, it's just 1 tick mark. But when I go up 1, it's up these whole big space. So I have to bear that in mind. So 1/5, starting at this point, I'm going to go up 1. And then to the right 5 spaces. So basically the point 5, 2 is what I want to graph here. Okay, that looks good. And then I can keep going to the right because I have 5 more here. So I want to graph 10, 3 because that is up 1 from 2 and to the right 5. Okay. And then I can go down 1 and left 5 as well. That's a nice easy point to graph. And oh, I think I have a piece of cardboard here. So I'm going to use that kind of as a straight edge to help me graph this oblique asymptote. And again, since I'm working without a grid, you can see my points don't perfectly line up. So I'm going to trust these 3 a little bit better than that one all the way out there. But this is my oblique asymptote. Let's carry it down. There we go. So again, since the slope was 1/5, I started at the y-intercept. I went up 1 to the right 5, up 1 to the right 5, or you can go down 1 to the left 5, and so on. All right, so that is the set of points that we have in our asymptotes. Now we have to use these to guide us. These vertical asymptotes that we have in blue can't be crossed. So I know, for example, it's either going to go up forever as I get close here and then maybe get up here. Maybe it goes up here and then swizzles down and comes here. Maybe it goes like this. Maybe it goes like this, like a little swizzle. So it could look either like kind of like a U or an upside down U, or it can look like a little squiggly, kind of like the x cubed, but not quite. On the ends, that's where the red line comes into play. So horizontal and oblique asymptotes come into play for the end behavior. So let me see, do I have a pencil nearby? I have a bunch of pens over here, I do have a pencil. So let me grab that. Should have prepared before I hit record, huh? So when I think about how to graph using this oblique asymptote, I've got a vertical asymptote here and then the oblique asymptote on the right. So this is telling me that my graph is going to look like one of two things. Either it's going to kind of follow this path, or it's going to follow this path here. Those are the only two options that I can have. Notice that if I follow this top path, it never crosses the x-axis. It always remains positive. And if I follow this path, at some point, it's going to cross the x-axis because it has to continue to go negative. So if I look at my table of signs, to the right of 3, which is where that asymptote is, it's always positive. So of these two options, I have to pick the one that will always be positive. This one is going to dip below the negative axis, or dip below the x-axis and become negative at some point, so I can't use this one. Now, I don't know any points up in this region since they didn't tell me, so I'm going to graph the function up there, but I'm just going to essentially use some guidance here. So I know it's going to get close to this vertical axis, and at some point it's going to turn around and start to follow this oblique asymptote. When I graph on the left-hand side, there's a similar sort of thing of options. I'm trapped between this line and the oblique asymptote. So either I'm up here and I cross the x-axis like past the 6, or I'm in this section here and I cross the x-axis in between where the blue and the red hit. And I can see by my x-intercepts, that's going to be what happens. So by looking at this, I'm going to expect it probably is going to look like that somewhat. So it's going to go through those 2 points, be positive between -2 and -3, negative between -1 and -2, and after -3. So let me see if that follows our table of signs. And it does. It's negative to the left of -3. So we're going to be kind of heading in this direction. It's positive between -2 and -3. So that's this little hill up here. And then it's negative between -1 and -2. So that's this coming down, getting closer to that vertical asymptote. So don't be afraid to kind of pencil things in lightly to kind of get a sense of what it would look like. You want to use your asymptotes as kind of the guides, like they're the walls that trap the function, if you will. So I know I'm down here, I'm positive between these two, so I'm just going to connect them. And then as I head towards the left, I'm going to have to get closer to that line. And as I come down in this direction, I get closer to that vertical asymptote. So now I've taken care of the left-hand side and the right-hand side. That's the use of the oblique asymptote. What happens in the middle with that oblique asymptote can be anything. You can cross it in the middle. you can ignore it in the middle, basically. It's just going to depend on what that table of signs tells us. So my asymptotes now are between -1 and 3, and I notice there's this x-intercept of 2 here. So between -1 and 2, it's positive. So that kind of makes sense based on our y-intercept here. So between this point and this one, it's positive, so it has to be above the x-axis. That means as I'm approaching this asymptote, it's going to have to be going up forever, because if it turns around, at some point it'll be negative. So I'm just going to draw a vertical line here, do a little swizzle there. And then between 2 and 3, it's negative. So that means we're going to cross at this x-intercept and go down in this direction. So when we have our vertical asymptotes, we approach those vertical asymptotes, but notice we don't cross over them. The oblique asymptote can be crossed in the middle, as it is here. That's totally fine. But on the ends, the function gets close to that oblique asymptote. So the next example I'm going to do only has vertical and horizontal asymptotes. I didn't give us a table of signs, so we'll have to create one based on the information provided. So let's go look at the next example. Okay, so here is our second example of graphing a rational function. Once again, they've given us a bunch of information, and then they want us to sketch it. So for this one, I'm just going to go ahead and plot the points they tell us. They tell us some intercepts, as well as some particular points it's going to go through. And again, if you want to pause the video here and copy down that information, feel free to do so. But I might be able to fit it all on screen at once this time. Okay, so I've got a plot 0, 2, 6, 0, so that's my x-intercept. My asymptotes are x is -3, x is +3. Remember, x equals is vertical. It's like backwards from how you want it to be, right? Because the x-axis is horizontal and the y-axis is vertical. But with the equations, it's flipped. If you see x equals, that means it's vertical, and y equals is horizontal. So our other asymptote is y equals 0, which is the x-axis itself. Then we go through the point -4 and -4. Right around here. 4, -1. So here's -1. And then 8, 1/2. So if this is about 1, then half of that's about here. Okay. So just by looking at this, I kind of have a sense of how this is going to sketch out. But let's create our table of signs so that we can get a sense of what's going to happen. We're going to use the x-intercepts and vertical asymptotes to create our table of signs. So we have an x-intercept at 6, 0, and then we have 2 vertical asymptotes. So I know I have my 3 separators here. And then in order, we have -3, 3, and 6. So I can tell that either from the information given or from what I have graphed so far. Then -4 is to the left of -3, and the result was negative. Between -3 and +3 is 0, and I see it's positive there. Between 3 and 6 is 4. I see it's negative there. And after 6 is 8, and I see it's positive there. So that just gives me some information to go ahead and use that to graph. So in this case, before -3, it's negative. So we've got this point here. What that means is I can't go up forever at this asymptote because that will require crossing the x-axis. So that means in terms of direction, this is going to come down this way. And then because I have this horizontal asymptote, I know that eventually off the paper here, it's going to be sort of flattened out. So I'm going to sort of try and get this to curve that way. There we go. So that's the section in this quarter here. Now I'll point out, if instead of -4, -4, we had had -4, +4, it would look like the reflection of this. It would be kind of in this section here. Then we know between -3 and +3, it's positive. So that's this guy here. So what this means is we know that this is not going to do the swizzle that the last one did. That's not the formal name. It's just I don't know what else to call it, right? So it does this little whoop, this little swizzly action here. So we know in this graph it won't do that because there are no x-intercepts here. So there are no opportunities for this to swizzle and come down, because if it did, it would cross the axis there. So that means we're sort of stuck here, trapped between the x-axis, not because of the horizontal asymptote, but because of the signs that we have up here. So we're stuck between here and going up. So I'm just going to make this sort of a U shape, going up forever on either side. Then between 3 and 6, it's negative. And we have this point here that helps us to graph. So I know from 6, it's going to connect down here. We can't cross the vertical asymptote, so it's going to get closer to that. And then after 6, it's positive. But this one is kind of strange because it doesn't become positive and go off to infinity here. We have this horizontal asymptote of y equals 0. So just like I knew this piece here had to approach the x-axis because of that horizontal asymptote, I know that has to be the case here as well. So it's going to kind of come up and then turn back around and get closer to that asymptote. So this is another example of what graphing a rational function can do. Again, you use your vertical asymptotes and your table of signs to kind of figure out what happens in the middle here. So because we were positive in this region, that's why we had this U shape. And then on the extreme ends to the left and to the right, you use both that vertical and in this case horizontal asymptote to guide you. So the horizontal asymptote said to the left of -3, it's got to be negative. So that's why it was down here. If it was positive, it would have been this shape up here. And then this one, we had a couple things to deal with. Between 3 and 6, it's negative. So we had to kind of construct down here. And then the positive, this one was tricky with that horizontal asymptote. So it kind of goes up a little, but then has to come back down to get closer to that horizontal line. All right, let's do one more example of a rational function that does not have like this middle piece. In other words, it's only going to have one vertical asymptote, which can also make things a little bit tricky to sketch. Okay, so this one we have g of x as a rational function. We have 3 intercepts. We know a point that it runs through, and we have the 2 asymptotes. So once again, if you want to copy down this information, you can pause to do so. And then my x-axis and my y-axis are very different on this one. So I'm going to have to zoom out just a smidgen, I think. There we go. So my vertical axis goes from -10 up to about 30, and I counted by 2s or by 4s, depending on how you think of the counting. And then each of these lines is 1 here. And I did that because the y-intercept is 0, 20, and it also goes to the point 5, 15. So I knew this vertical asymptote, or vertical axis rather, is going to have to be pretty big. So let's go ahead and graph the points that we know. That'll be the easy part first. So we go through -5, 0. We go through 0, 20. And we go through 2, 0. And then the other point that they gave us was 515. So I'm going to do my best here to try and guess where that is. Okay, so if that's 12, that's 14. So here's 16. Here's 14. So 15 will be in between. So 5, 15. Okay. Again, if I was doing this on graph paper, it would be a lot easier than freehanding it. But, you know, we're doing our best here. Okay. So those are our 4 points. We also have a vertical asymptote, x equals 1. So we can sketch that out. Okay. Then before we can connect the dots, we're going to graph our oblique asymptote, which is y equals 2x plus 8. Remember, you can think of the slope as rise over run. So I'm going to put this as 2 over 1. And the plus 8 tells us the y-intercept is at 8. So I'm going to plot the point 0, 8. And then I go up 2 and to the right 1. So each of these lines is 2, and each of these lines is 1. So it's going to look like it has a slope of 1, actually, because of how the things are sort of, so what I'm looking for, how they're scaled here. So 3, there, 4, 16. Okay. The further I am from the axes, the harder this becomes. And then I'll go down 2 and left 1. Over here. All right, and you don't have to plot all these points, just whatever you can plot to help you graph it. And then I'll bring my cardboard here and connect them. Oh, some of these are way off. Oops. Again, we just kind of did our best here. Okay, there we go. All right, so now we have all the pieces that we need in order to graph this rational function. So there are 2 sections of this graph. This vertical asymptote essentially separates them out. So if I think about like the quadrants, they're not equal, so they're not quite quadrants. But on the right-hand side of this graph, I'm either going to have a piece in this upper triangle or a piece in this lower, whatever that is. Okay, so I've got to be bound on the left by the asymptote and on the right by the red asymptote. And whether I live above the red line or below the red line is going to be determined by the points we have graphed. So I notice that I've got this blue point and this blue point here. So that means I'm going to kind of follow this path through here and continue going down in this manner. Now, I would like to have another point, perhaps between 2 and the asymptote, but they didn't give one to us. So I'm going to follow kind of what seems to be happening here. And then I'll do the same thing on the left-hand side of this asymptote. You kind of have to ignore the axes in this case. So they're standing out here bold at us, but they don't define kind of where we live. The asymptotes do. So again, this asymptote and the red asymptote, we've got kind of this wide space up in here, or we have this narrow triangular space. Again, because of the points that we have plotted, it's telling me this is going to go up in this manner and get closer down underneath here. So go up in that manner and then down over here towards that asymptote. All right, so this is our 3rd example of graphing a rational function. And all 3 of our examples, the final graphs look pretty different. So you want to use intercepts as your guide. You want to use asymptotes as your guide for extreme behavior. On this one, because we only had one vertical asymptote, that's really the only place where the information gets broken up. And so we had this piece here that was guided by the red line and the blue line. And then this piece on the left, again, guided by the red and the blue and the points that they told us. All right, now we're going to do 3 examples of how to solve some nonlinear inequalities. Okay, this first nonlinear inequality is set up as a domain type question. It says, let's find the domain of f of x equals the square root of 5x plus 6 minus x squared. So when you see domain, right now there are 2 things that should jump to mind. The first is that denominators cannot be 0. And then the second is that inside an even radical has to be greater than or equal to 0. If you don't have a denominator and you don't have an even radical, the domain's going to be all reals. In this case, we have an even radical since we have the square root. So this is going to be the setup we need to take. So I have to take whatever's underneath that radical and make it greater than or equal to 0. So I'm going to take my 5x plus 6 minus x squared, and I want that to be greater than or equal to 0. Now, when you are solving a nonlinear inequality, our goal is to get everything all together on one side and then hopefully factor. We're going to create a table of signs in this case. If we cannot factor, then because we have a quadratic, we could use the quadratic equation. So one thing I'm noticing is that I've got this -1 over on the left in front of that x squared, and I want to put this left-hand side in standard form, so the x squared is first. So I'm going to multiply both sides by -1 just so that I get a positive x squared instead of a negative x squared. Now this is a dangerous thing to do with inequalities because remember, whenever you multiply or divide both sides by a negative, the inequality symbol has to change directions. So I'm going to distribute this. A minus 5x minus 6 plus x squared is now less than or equal to 0 since I multiplied by a negative. And now I can rearrange this so it looks like a normal quadratic. X squared minus 5x minus 6 is less than or equal to 0. Okay, so again, because I had an even root, the inside stuff had to be greater than or equal to 0, and now I'm just rearranging it so it looks like something x squared plus something x plus something. Now I'm going to factor here. I need 2 numbers that are going to multiply to -6 coming from here and add to -5 coming from the b coefficient. And -6 and +1 are going to work, right? -6 times 1 is -6. -6 plus 1 is -5. So this will factor into x minus 6 and x plus 1. Now I'm going to create my table of signs using each of these factors. So if I have x minus 6 equal to 0, that means that x is going to have to be 6. And if I have x plus 1 equal to 0, that's going to mean x is equal to -1. So these are not solutions to the inequality, but they do tell me where like the ending points are going to be. So let's create our table of signs. We've got -1 and 6. Now, as you do more of these more frequently, you'll find some shortcuts you can take, but I'm just going to plug them in and see what I get. So I'm going to pick -2, 0, and 7. Again, only because -2 is a nice number to the left of -1, 0 is a nice number in between, and 7 is above 6. And I'm going to plug them into my factored form here. So -2 minus 6 is -8, and -2 plus 1 is -1, which is going to give me a positive 8. So to the left of -1, it's positive. If I plug in 0, I'll get -6 times 1, which is a -6. And then when I plug in 7, I'm going to get 1 times 8, which is a positive 8. So we're positive. And then also, these were my x-intercepts. So I'm going to put a dot there in case we have an or equals to. Okay, so just to recap what I did, I took my factors, set them equal to 0, and where those values that I found, those I'm going to plot for my table of signs. And then I picked a number smaller than -1, a number between -1 and 6, and a number bigger than 6. That's where I got these 3 from. And then I plugged them into here. Now, in this case, we want our solution to be less than or equal to 0 because this is the thing that we're solving. So less than or equal to 0 means I want a negative number. So I'm going to be between -1 and 6, and because of the or equals to, I'm going to include those. So for my final solution, I'm going to have -1 to 6, and it's included. All right. Okay, so to find the domain, we didn't have a denominator, but we had an even root. So this thing that was inside had to be greater than or equal to 0. I multiplied both sides by -1, being careful to flip this inequality. I did that so I would have a positive x squared. If I already had a positive x squared, I wouldn't have multiplied by -1, right? I factored, made my table of signs, and got my final solution. Let's do another inequality, and this time we'll have some rational expressions. Okay, so this example says, let's solve 2x plus 1 over 3x plus 9 is less than or equal to x minus 5 over x minus 3. Whew. Now, you have to avoid the temptation to cross multiply. If this was an equal sign, it would be a perfect proportion. We could cross multiply, no problem. But because it's not an equals to, we can't. The reason we can't is because we don't know what the value of x is going to be. So if x, for example, is 1, if I put 1 in here, then I'm going to get a negative number in the bottom. So I'll be multiplying both sides by a negative, so this would have to change direction. So since we don't know what x is, we can't cross multiply because we don't know what that impact that will have on the inequality sign. So instead, we're going to bring everything over to one side so that we have 0 on the other side, and then create a table of signs. So we could bring everything to the left, or we could bring everything to the right. You know what, yeah, this time I'm just going to bring everything to the right. But again, it really does not matter how you decide to do this. So I'm just going to subtract this thing from both sides. That'll get me 0 is less than or equal to x minus 5 over x minus 3 minus 2x plus 1 over 3x plus 9. Okay. Now, in order to solve this, I want to have 0 is less than or equal to a single rational expression. So I'm going to need to get a common denominator so that I can combine these two into one fraction. The easiest way to do that here is to multiply top and bottom of this rational expression by the other denominator, and then vice versa, this rational expression by this first denominator. So I'm going to multiply top and bottom here by 3x plus 9. And then I'm going to multiply top and bottom of this one by x minus 3. When you do this, you want the top to become a mess, but the bottom to remain factored. That's because when you add or subtract fractions, the bottom stays the same. It won't change once it's common, But the top, you have to combine things together. That's where it changes. So ultimately, we want everything factored form if we can. So let's just keep the bottom in factored form. So this is going to be x minus 3 times 3x plus 9. And if that bothers you, if you want to pull the 3 out of here, you can. I don't think it's going to make a difference for this one. 3x plus 9 and x minus 3. And remember, order doesn't matter so much here. Now, on the top, x times 3x is 3x squared. Then I'm going to get 9x minus 15, should be minus 6x. And then minus 5 plus 9 is minus 45. On this right one here, 2x times x is 2x squared. Minus 6 plus 1 is minus 5x. And 1 times negative 3 is minus 3. Okay, so there's our distributing. Now I'm going to go ahead and subtract the numerators. Now, I'm notorious for making mistakes in subtraction. So a habit I learned is I'm going to change subtraction to plus, and then I'm going to change the sign of everything over here, and now think of it as like an addition. So 0 is less than or equal to 3x squared plus a minus 2x squared is just an x squared. Minus 6x plus 5x is minus x. Minus 45 plus 3 is minus 42. Over x minus 3 and 3x plus 9. Okay, now, looking better. Denominator is in factored form. Let's work with the numerator now. So in the numerator, basic quadratic with a leading coefficient of 1. So we're looking for two numbers that multiply to a negative 42, but add to a negative 1. So since they add to a negative, that means they have to have different signs, and they have to be different by 1. So this one is going to be, looks like a positive 6 and a negative 7. So 6 times negative 7 will be negative 42. That's how we knew they were going to be different, the negative 42. And then the negative 1 says the bigger number is negative. So we have 0 is less than or equal to x plus 6, x minus 7. And now at the end, I'm going to factor that 3 out of here. I'm just going to pull it all the way out front. And when I do that, this is going to become an x. And then factoring a 3 out of 9 gets me a 3. Whew, okay, we're looking good. So now we are going to create our table of signs, since the top is factored and the bottom is factored. When you create your table of signs, you have to pay attention to intercepts as well as asymptotes. So the top is going to give us intercepts, and the bottom is going to give us asymptotes. Well, vertical asymptotes. Okay. We don't care so much about horizontal or oblique asymptotes for our table of signs, because where that horizontal or oblique asymptote isn't going to change whether our result is positive or negative. But we can change direction at intercepts, and we can change direction at asymptotes. So that's why we care about those. So our intercepts are going to be at negative 6 and at positive 7, as well as positive 3 for our asymptote and negative 3. The reason I'm changing the signs here is because you would do x plus 6 equals 0. So when you subtract 6 from both sides, you get that negative. Same thing here, x minus 7 equals 0. When you add 7 to both sides, you get a positive. And same thing with the asymptotes here. So I'm going to have 4 spots on my table of signs. And I want to put them in numerical order. So negative 6, negative 3, positive 7. And with rational expressions, it's really important to know where my intercepts are versus where my asymptotes are. So I'm going to put little dotted lines to indicate my asymptotes, and I'm going to put points to indicate my intercepts. Okay, now in the previous example, I plugged in numbers and kind of got my result that way. This time I'm going to do a little bit of a shortcut. I'm going to plug in, I'm going to start on the positive side because it's easier to deal with positives. So let's pick 8. 8 and 6 is positive. 8 minus 7 is positive. 8 minus 3 is positive. 8 plus 3 is positive. So this whole thing is going to be positive. Pick a number between 3 and 7. 5. 5 plus 6, positive. 5 minus 7, negative. 5 minus 3, positive, and 5 plus 3, positive. So it looks like I'm going to get a negative over a positive, which is negative. Pick a number between negative 3 and 3. 0. So 6, negative 7, negative 3, positive 3. These negatives cancel and I get a positive, so we're positive in here. So this little shortcut helps you to kind of do a little bit more mental arithmetic. You don't have to figure out the exact numbers. All we care about is the sign, whether it's positive or negative. If you're more comfortable putting a number in and just kind of plugging it into your calculator and checking, that's totally fine too. There's nothing wrong with that. But if you feel comfortable with this kind of method, you don't even have to write it down. I'm just doing so you can kind of track my work. So if you're comfortable with this method, feel free to use it, okay? So between negative 3 and negative 6, let's go with negative 4. Negative 4 plus 6 is a positive 2. Negative 4 minus 7 is negative. Negative 4 minus 3 is negative. And negative 4 plus 3 is negative. So we get some negatives canceling. So I get a positive over negative, which is a negative. And by the way, if you're wondering why I'm ignoring this 3 out front here, that's because it's a positive 3. And if you multiply anything by a positive, it won't impact the sign. Right? If this was a negative 3, I'd have to pay attention to it. But since it's positive, I get to kind of ignore it. If you want to, you could think of it as just being a positive here the whole time, down in the bottom. And then something bigger in the negative direction than negative 6. So let's go with a negative 7. So negative 7 plus 6 is negative. Negative 7 minus 7 is a negative. Here's our positive 3. Negative 7 minus 3 is a negative 10. Negative 7 plus 3 is a negative 4. So these cancel, and we get a positive. Okay. So here's our table of signs. It looks like we flip-flopped at each opportunity. Great. Now we have to figure out what it is we're looking for. So we have 0 is less than or equal to this mess. So that means this mess is bigger than 0, meaning we're looking for the positive components. So I'm interested in this piece, and this piece. So we have negative 6, so I'm looking for negative infinity up until and including negative 6 because of the or equals 2. Between the 3 and negative 3, but because we had our asymptotes there, it doesn't exist there. So we're going to have negative 3 to 3. And then from 7 off to infinity, and because 7 was an intercept, we're going to include that. So, that is our solution to what looked like it was going to be a simple cross multiplication, but in the end turned out not to be. All right, so let's do one more that involves polynomials. All right, oh, excuse me. So for this example, we're going to solve x cubed minus 5 is less than 3x times x plus 3. So our goal here, whether we have rational expressions or polynomials, because this is not linear, we have this x cubed, we're going to get an x squared from this product. We want to bring everything all together on one side. So I'm going to start by distributing this 3x on the left to see where the higher degree is. So we have x cubed minus 5 is less than 3x squared plus, looks like 9x. Okay. Now I notice I have a cubed on the left, and I like when that coefficient is positive. So I'm going to keep that there. So I'm going to bring these guys over to the left. So everything will come to the left, and we'll have 0 on the right. So I'm going to subtract 3x squared and subtract 9x. Minus 3x squared minus 9x minus 5. And this is less than 0. So I'm sighing because I was hoping there would be some grouping, but there isn't. I mean, I could try and arrange it so these two got grouped, but 3 goes into 9 3 times, and I can't factor something out of x cubed and 5 to get like a 3. So this is looking like I'm going to have to use our factoring techniques that we've been practicing for polynomials. So let's find some rational number candidates. We're going to do the C over L thing, the rational zeros theorem. So we need C for the constant term, so factors of 5, which are just 1 and 5, and factors of the leading coefficient, which is a 1. So not too bad. My options are either going to be 1, -1, 5, or -5. Hello, my friend. Let's see what the calculator can say for us. So let's plug in 1 cubed minus 3 times 1 squared minus 9 times 1 minus 5. Okay, that gave me a -16, so that won't work. Let's try -1. -1 cubed minus 3 times -1 squared minus 9 times -1 minus 5. So I'm plugging into the polynomial here. Ha! So that's my candidate. Let's go ahead and divide by that, and then we'll come back up here. So yeah, I guess I can kind of figure out how to work this. Do my synthetic division over here. So here's my -1 and my coefficients. We've got 1, -3, -9, -5. -1 times 1 is -1. -3 minus 1 is -4. -1 times -4 is a +4. -9 plus 4 is -5. -1 times -5 is +5. That will get me a 0. So when I factor out x minus -1, or x plus 1, I'm going to be left with x squared minus 4x minus 5. All right, so now I have a quadratic, which hopefully we can factor. We can do so if we find two numbers that multiply to -5 here, but add to -4. So multiplying to -5, my options are 1 and 5. So if they add to -4, we've got -5, +1. That'll get me that -4. So here's my x plus 1. Then I get x minus 5 and x plus 1 again. Since x plus 1 appears twice, I can group them together as x plus 1 squared and then x minus 5. Whew. Okay, let's recap for a moment. We took this guy, we had to get everything together on one side. So I distributed the 3x and then brought everything to the left to keep this a positive x cubed. We used the rational root theorem to identify good candidates, and then applied synthetic division to get our first factor of x plus 1 and the second factor. This was a quadratic that factored nicely, so we went ahead and factored it. We had a repeated factor, so we grouped that together. So far, none of this is any different than if we were solving this with an equal sign here, right? If this had been equals, all of these steps would have been identical. This last step is where things change. Because of the less than sign, we're going to make our table of signs. We only have two roots, one at -1, the other at 5. And again, I would take this like x plus 1 and set it equal to 0. That's how I got -1. And I would take this x minus 5, set it equal to 0, and that's how I get x equal to 5. So that's how I'm getting the values here for this table. And now I'm going to plug in numbers and see whether I get a positive or a negative. I'm also going to fill in the circles here because that's where we equal 0. All right, so let's say I pick -2. I'm going to get a negative. If I pick 0, I get a negative. And if I pick 6, I get a positive. Here's how I was able to do that so quickly. See how this is a squared? That means no matter what number that's in here, I'm going to get a positive. So really my shortcut is just to look at x minus 5. So -2 minus 5 is negative, 0 minus 5 is negative, and 6 minus 5 is positive. Again, it doesn't matter if you notice that trick or not. If you don't notice it and you plug numbers in here, you're going to get exactly the same signs. It'll just take you a little bit longer. And there's nothing wrong with it taking a little bit longer. That was a little Freudian slip there, I guess. But honestly, like, it doesn't matter. If you find tricks and you are comfortable using them, go for it. If the tricks make it more confusing, then go through the by the book, by the definition method, because that will always serve you and always guide you. That's what all that properties and tricks are in math, is they're just shortcuts. And if you know a definition and follow it, it will get you to where you need to go. So we are interested in when this expression is less than 0. So we are interested in these negative pieces. Now we have to be careful here, because at -1, we equal 0. We don't have an or equals to here, so we can't include that -1. So we're going to include everything before -1. We're cutting it out. Everything after -1 up until 5. And we don't include the 5 again because we don't have the or equals to. All right, and there we go. That is our next inequality. So if you are looking for some guidelines for solving nonlinear inequalities, I would say they are first, get everything together on one side by like adding or subtracting stuff. That's what we did here. And that's also what we did in the previous example. We brought this 2x plus 1 over 3x plus 9. We subtracted it to the other side. You want to avoid multiplying or dividing by anything with an x, because if you multiply or divide by something with an x, that could inadvertently impact your inequality symbol. So you get everything to one side so that 0 is on one side, everything else is on the other. And then you try to factor if you can, or you get your rational expressions as one thing. You create your table of signs, and then you try to decide, do I want the positives or negatives? So here we want to be less than 0, so we want to be negative, so that informs our solution. All right, so that's going to wrap that up for this video. If I receive any more emails before Thursday night, I will either type up some more examples or maybe film another short video if I have some time. I hope you're all staying warm and safe during this snowy time, and I will see you hopefully next week on Tuesday. Have a great day, everybody. Bye-bye.